Remember the ideal gas from science class? That super perfect, totally predictable model for how gases are supposed to work? Well, what if I told you it's kind of a myth? Today, we're going to dig into why that is.
Yeah, I want you to think all the way back to chemistry or maybe physics class. You definitely learned about gases that followed all the rules, right? They behaved in these perfectly predictable ways. But what if that whole perfect model was really just a handy shortcut? A useful story for sure, but definitely not the whole story. And that's exactly where we're headed.
All right, so let's get on the same page. The official textbook definition of an ideal gas is basically a theoretical gas that follows all the rules, like Boyle's law, Charles's law, just perfectly. It's super clean, really simple, and it makes all the math a breeze. You know, in this perfect little bubble, gases are always predictable, always well-behaved. The key word there, though, theoretical. And this is the big reveal right here. In the real world, no gas is actually ideal. Not one. They all stray from that perfect behavior, especially when you put them under certain conditions. So yeah, the ideal gas is a scientific myth. A super useful one, don't get me wrong, but a myth all the same.
Okay, so this is where it gets really interesting. If the model isn't perfect, then you gotta ask, right? Where and why does it fall apart? When does reality come along and just crash the whole ideal gas party?
And here we go. This lays it out perfectly. On one side, when you have high temperatures and low pressure, real gases do a pretty good job of pretending to be ideal. They're close enough. But look at the other side. When you drop the temperature way down or you crank up the pressure, that's when they start to go rogue. They deviate, and our simple little model just can't keep up. Now, this isn't just random chaos. The fact that they deviate in these specific ways points to a fundamental flaw in the original theory. I mean, if a model only works some of the time, that tells you that some of its basic assumptions have to be wrong. So the big question is, what exactly did the theory get wrong? Well, this brings us to our hero, a scientist named van der Waals. He's the one who really looked at these deviations and had that aha moment. He realized that the classic theory of gases was built on two very specific and, as it turns out, very wrong assumptions. And here they are, the two big flaws, laid out nice and clear. First, the ideal model assumes that gas molecules feel absolutely no attraction to each other, none. Second, it assumes that the molecules themselves are just tiny little points that take up zero space. And as we're about to find out, both of those ideas are just wrong. All right, let's dive into that first flaw, this myth of no attraction. The theory basically pretends that gas molecules are completely indifferent to each other. You know, like strangers passing on a super crowded street who just never, ever make eye contact or interact at all.
Now, to be fair, at really high temperatures, this assumption is, well, it's almost true. The molecules are just buzzing with kinetic energy. They're moving so incredibly fast that any little tug of attraction between them gets completely ignored. They just zip right past each other. But the moment you start to cool things down, they start to slow down. And all of a sudden, those tiny forces of attraction that we ignored, they start to matter a lot.
It's exactly what this says here. When you lower the temperature, you're taking energy out of the system. And that means those intermolecular forces, think of it like a natural stickiness between molecules, suddenly become a big deal. The particles start to actually pull on each other, and they get closer. And here's the ultimate proof, the real kicker. It's something we see all the time. How do we get liquid nitrogen or liquid oxygen? We make the gas really, really cold. The simple fact that gases can turn into liquids is the absolute undeniable proof that their molecules attract each other. Think about it, if they didn't, they would never be able to clump together to form a liquid. It just wouldn't happen, no matter how cold you made them.
Okay, so flaw number one is busted. Let's move on to the second one, the myth of zero volume. This is the idea that the gas molecules themselves are just these tiny, tiny little dots that take up literally no space.
And again, at low pressure, this is another one of those assumptions that's, well, it's good enough. It's like having, say, 3 marbles in a gigantic warehouse. The actual space those marbles take up is basically zero compared to the size of the whole building, right? You can ignore it. But what happens when you crank up the pressure? That's not marbles in a warehouse anymore. That's like trying to cram 1,000 bowling balls into a tiny little closet. All of a sudden, the space the bowling balls themselves occupy is a massive part of the picture. You absolutely cannot ignore it.
So that's the bottom line.
When you squeeze a gas into a smaller and smaller space, you just can't pretend the molecules are dots anymore. Their actual physical volume starts to take up a real chunk of the container's space, and our ideal model, which is built on ignoring that fact, just completely breaks down.
Okay, so we've found the two big cracks in the foundation of the perfect gas model. So what? Why does this even matter for real-world science and engineering?
Well, it matters because by fixing these two seemingly tiny assumptions, by finally admitting that yes, molecules attract each other, and yes, they take up space, we can build a way more powerful and accurate model. This is what lets us predict how real gases behave in the real world under real conditions. I love this analogy. It's like the difference between a simple subway map that just shows you the stations and a detailed satellite photo that shows you the entire city. Both are useful for sure, but one is a heck of a lot closer to reality.
And you know, this whole thing points to a much bigger idea about how science actually works. The goal isn't always to find some perfect, unbreakable law that's set in stone forever. A lot of the time, it's about making things better and better. We start with a simple model, like the ideal gas. We push it until we find its breaking points, and then we use that knowledge to build a better, smarter model that gets us one step closer to understanding our messy, complicated, and frankly, beautiful reality. So I'm going to leave you with this question to chew on. The ideal gas was a brilliant starting point, but reality, as it turns out, is always a bit more complex. And it really makes you wonder, doesn't it? What other perfect models are we using every single day? Maybe in economics or psychology, or even in how we think about our own lives. What other useful simplifications are just out there, waiting for us to take a closer look and account for the messy, wonderful truth?